We're going to use solubility products, KSP, to predict when we can precipitate something in the presence of a common ion. So we have a first simple problem here where we ask what is the maximum chloride ion that can exist in solution containing 1.0 molar silver nitrate before we precipitate silver chloride. And then we're going to make it more complicated by coming down here and looking at this problem down here where we have a mix of silver nitrate and lead nitrate, and we're going to figure out which one will precipitate first if we start dripping in some potassium chromate. So we're going to do the top one first. So I've got the rice table set up here with silver chloride in equilibrium with the respective ions, and we're not going to pay any attention to the solid silver chloride. We've been told that our initial concentration for the silver ion is 0.001 molar, and then we want to see how much chloride we can add. So we don't have any to start with. We're going to add some of the chloride ion as the silver chloride dissolves. Our equilibrium concentration is 0.001 plus X and X. We are going to assume that X is tiny versus 0.001 molar, and that makes sense because 1.6 times 10 to the negative 8th is a very small number. So we have that 1.6 times 10 to the negative 8th is approximately equal to 0.001 times the chloride ion concentration. So when we solve for X, X is equal to 1.6 times 10 to the negative 5th. So what does this mean? Well, what it means is that when our chloride ion concentration exceeds 1.6 times 10 to the negative 5th molar, silver chloride will form. Okay, so that's a very straightforward problem. Let's try the more complicated one underneath. We have a mix of 0.20 molar silver nitrate and 0.20 molar lead nitrate. Both of these are very soluble because of the nitrate ion. What we're going to start doing is dripping in potassium chromate. So we've got silver ions and lead ions and nitrate ions, and we're dripping in potassium chromate. The potassium chromate will form precipitate with both the silver and the lead. And what we need to figure out is which one is going to precipitate first. So what we need to do is we need to calculate the chromate ion concentration, CrO4 2-, to begin precipitating both of the particular compounds. So we're going to first calculate for the silver chromate, and then we'll follow up for the lead chromate. So for the silver chromate, our KSP is equal to 9.0 times 10 to the negative 12th, and this is equal to our silver ion concentration squared times the chromate concentration. So we're going to substitute in the concentration for the silver. So 9.0 times 10 to the negative 12th is 0.02, and I'm leaving off the trailing zero just so the calculation fits on the page. Okay, so when we calculate the chromate ion concentration, where we will begin to see precipitation, if the chromate concentration is either greater than or equal to 2.3 times 10 to the negative 8th, then we will start to see precipitation form. So precipitation will start. All right, now we're going to return to the lead chromate. And I've already started this down here. So the KSP is 1.8 times 10 to the negative 14th. That's equal to the lead concentration times the chromate concentration. So we're going to plug in the concentration of the lead 2 plus and solve for the chromate ion concentration. And in this case, if the chromate ion concentration is greater than or equal to 9.0 times 10 to the negative 13th molar, then precipitation begins. So we have two values that we need to compare. We need to compare 2.3 times 10 to the negative 8th and 9.0 times 10 to the negative 13th. So we're dropping in drop by drop here. So what we're looking for is the one that precipitates at the lowest amount. So CrO4 2- will precipitate the lead first. So you have to go through and do both of the calculations and then compare your two values, and whichever one will begin precipitating at the lower concentration, that's the one that will precipitate first. And actually, let me finish this off and say as lead PbCrO4. Okay.